I want to talk about in general fiber reinforced cement based composites, and I want to give some historic perspective where we are today and where we could be going. And after the RILEM conference, what is the basis of current development? So it's essentially a 50-year history. And why 50-year? You will see that my first paper on fiber reinforced concrete was published in 71. So what are the precursors of current development? So there are, I have identified 4. Started with steel fibers in US, then glass fibers in UK primarily to replace asbestos fibers in cement board, then ferro cement in Italy by well-known architect and engineer Pierluigi Nervi, which is a precursor of currently textile reinforcement, and extrusion, which can be considered precursor for 3D printing. So let me first start with the development of steel fibers in US, and the concept behind the development, according to Ramualdi and Batson, they were at Carnegie Mellon, is that concrete is a brittle material, and a brittle material obeys the Griffith fracture criteria, that is fracture strength is inversely proportional to flaw size. Smaller the flaw size, considerably higher fracture strength. So they said that if you use fibers, randomly distributed fibers, they can be closely spaced, so you can increase the tensile strength. So very intriguing idea. And when they published their paper, I was doing my PhD at Cornell, and I got quite interested because I had taken courses in fracture mechanics when I was at Lehigh University. And I looked at the paper, and it turns out in order to prove their concept, they tested reinforced concrete beams which were with wires, and they were under reinforced. So as soon as the crack happened, the bar yielded. And to get same volume but closer spacing, they have to use thinner and thinner, smaller diameter wire. And when I looked at it, smaller the diameter of the wire, higher the yield strength. So when I normalized the results with the yield strength, it turns out there was no effect of spacing. Then that got started, and then we did some work with randomly distributed steel fibers. So here you can see I have percentage of fibers, and of course more volume of fibers, they will be closely spaced, versus tensile strength, and then what we call toughness is the area under the load deflection curve. And this was the work I did with Vijay Rangan, who is now retired from Perth. And you look at it and see there is really no increase in tensile strength, but there is a substantial increase in toughness. And in fact, if you look, why is that? One of the reasons why there is no effect of spacing, because at the meso scale, the cracks start at the micro level. So these fibers, which are macro fiber in millimeter range, and we are talking about 1% more or less. So before the fibers can interact with crack, micro cracks have already coalesced into macro crack. So tensile strength is already formed. Then they will constrain crack opening or crack width and toughness. So that is really the basic idea about the currently used fiber reinforced concrete. So if you look at the fiber reinforced concrete, whether it's in tension or compression, load versus deformation, so we know that normal concrete in compression or tension is characterized with this strain softening, very important part in compression especially, and in tension. So when we have fibers, and I am talking about a percent, it would not change the modulus. It really generally does not change tensile strength, but it does change substantially the post peak. So crack control is the main reason now we are using macro fibers, conventional fiber reinforced concrete. The toughness becomes important. So how to measure fracture toughness? Well, for linearly elastic fracture mechanics, there are ASTM tests. You have a notched beam, and then you apply the maximum load, apply the flexural load, and when it reaches maximum, everything is elastic. And from the peak load and this crack depth, you can calculate fracture toughness. But a lot of work has been done, and it turns out that fracture toughness, concrete is not quite brittle, we call it quasi-brittle. So crack propagation before the peak, there is so-called fracture process zone. So you cannot use LEFM. And so there is a lot of work done. I think that Professor Getru has been also involved. And now I think people conclude the best way to get experimentally the fracture toughness to have this notched beam test, and you test it in a crack mouth opening displacement. And when you say apply the load with a CMOD control rate, then you get entire load displacement curve, and from there you can calculate fracture toughness. So this is really a accepted way. Italians have a code based on this test. Now, not too many people can have closed loop testing. I know IIT Madras has it, but many people don't. So you need a method which is somewhat easier to conduct than the CMOD control. So we developed this so-called ring test. In a ring test, you have a concrete here, and there is a steel ring which is relatively rigid. So after curing, you put concrete into drying. So concrete wants to shrink, steel says no, so you develop tensile stress. And because of axisymmetric, it's like infinitely long tensile specimen. So you find out when the crack starts, and then using microscope how wide the cracks are. So this test now has been standardized by both ASTM as well as highway department in US. And it's a good way to have a crack potential of a material, evaluate different types of fibers. For example, we showed that when you make a high strength concrete, and when you compare it with normal strength, high strength would have a higher tensile strength, but because it's more brittle, it cracks earlier than normal concrete. So this is a very good test. And to show how it works, for example, I've shown you some results with steel fibers, reinforced concretes. Here is the volume of fiber, and there is average crack width. And you can see as small as 0.5% of fiber volume substantially reduces crack width. And this is why we are using crack control, photo control fibers, reinforced concrete. Now, when you cast concrete, those of you who have done experiment know that if you increase the volume of fiber, workability is the issue. If you increase the length of fibers, workability of issues. So this is one of the reasons why with the cast concrete, most of the application of fiber reinforced concrete, we are talking about 1% and aspect ratio not too much larger than 100. So people are looking at alternate methods of production than cast in place. One of them is this called head check process, which was developed in Australia, and it's widely used for so-called cement board. So cement board is, you have a very dilute slurry originally with asbestos fiber, and then layer by layer it's deposited. So this is in fact the first example of so-called adaptive manufacturing, because you have a layer by layer manufacturing and you get cement board. It turns out that asbestos could cause lung cancer called asbestosis. So many countries have banned. So people have been looking for alternate. So in England, they came up with alternate of glass fibers instead of asbestos fibers. And the pioneering work was done by Mazumdar at Building Research Institute in England. Now, when we use normal glass, there are issues with the alkali reaction of E-glass. So they developed adding zirconia called alkali resistant glass fibers. And it turns out that in these applications, glass fiber really did not work this processing. So now for head check process, people are using cellulose fibers instead of asbestos, cellulose fiber for green strength, and then for reinforcing either PVA or polypropylene. But chopped glass fiber spraying and simultaneously spraying with a slurry of cement and glass fiber has become quite popular, and it's called GFRC, glass fiber reinforced concrete. And let me show you some work we did with the GFRC. So when the alkali resistant glass fiber was developed to test that it doesn't corrode in the high pH, they do a test with a glass strand surrounded by high calcium hydroxide solution, and then measure it to see whether the tensile strength with accelerated test works. It's called SIC, and they showed that alkali resistant glass fiber in this test works very well. But when you make composite out of it with the glass fiber chopped, it turns out that because calcium hydroxide can go into the filament and make the glass fiber brittle, even alkali resistant glass fiber with the right environment can become brittle. So to show that we did this work, and I think this was sponsored by San Gobain, which also you are working with. So if you look at the 28-day, this is sprayed up glass fiber reinforced. So you have a linear behavior. People often call this bend over point, and then you have this nice multiple cracking and strain hardening response. And this is 4 to 5% of glass fiber. So with this technique, you can use longer glass fibers and higher volumes. So great response. Then we subject that to this accelerated, I think about 60 or 65 degrees in lime water, and you can see that there is a substantial degradation. So even though, the important point, even though with single SIC test, there was no degradation, in the composite there was substantial. And because I said the glass fibers, which is made with different filament, calcium hydroxide goes in and becomes brittle. So then there are other ways to solve this. You can use pozzolanic material so that there is less lime. But this is important to know. I know that I had talked with one of you who is working on textile, and I mentioned that he must also test the composite to see whether you have durable results. Now it's different with a continuous fiber rather than chopped, because when the chopped fiber is inclined, then they can break. So you might have a different mechanism with that. Okay, so that one way, there are two alternate that then cast in place that I mentioned. One was the head check process, and the second was this GFRC, where you spray glass fiber and cement, and both would allow longer fibers and higher volume, so you can get this strain hardening response. Well, third way, which is extrusion, and I talk about extrusion because it is precursor to 3D printing, and we developed this in 1997. So this is a screw type extrusion. You have fiber reinforcement, material looks like a dough, and you push it through a die, and depending upon the shape of the die. And the fibers we used here are, I call, microfibers. So they were PVA fibers, 14 micron in diameter, and rather short, 2 millimeter long. And you can see that we got 2% and 4%. We got a higher tensile strength because fibers can now interact with micro cracks. And if you design it right, you get a strain hardening response, because it's essentially like a ductile. So this, to show that, I often during that time I show this to my class. This, as you can see from the hair, it was a long time ago, 1987. But so this is the currently where we are in fiber reinforced composite. So most, as I said, some of my macrofiber is still the most commonly used commercially, but people have been working with this so-called strain hardening cement composite. And there, here is, for example, one of the, that what we did, which is a 10 megapascal and strain hardening response. So that is the what we are currently. Now, what we found out, if you recall, I told you that with the effect of closer spacing did not work with the macro fiber, but with the small fibers we have now. So what we did, we had this, all the material had the same volume of PVA fibers, but because of dispersion, other reason, we got different results. And so we cut the specimen and using SCM calculated what is the fiber free area, and assuming fiber free area is the flaw size. So here is, we calculated the fracture composite versus fiber flaw size, and we did get somewhat similar to fracture, Griffith fracture criteria. But the flaw size has to be in a small enough range, and the fibers have to be in the range size that they can interact with the cracks. So, and with extruded cement, I showed you this, depending upon the die you can manufacture sheets, and as a matter of fact, so-called cement board with different fibers have been extruded in Japan. You can even extrude pipes or the cellular wall. And to show you that how light there can be, this you might, many of you know Alva Pilet. She is a professor now at Israel, but she was a postdoc with me. And this is quite almost a 2 meter tall cellular section, and it's light enough that Alva can lift it. And Ilmaz, who is now a professor in Istanbul. So then there are other ways to manufacture, and one of the Alva and primary and Barzin Mubashir at Arizona State, they are using this pultrusion. Now pultrusion is quite common for resin and epoxy type of composite, but not, this is the first time with the cement. So you have a continuous strand, it goes through the cement slurry, and then you develop the composites. Okay, so another thing which is people have studied quite a bit is so-called hybrid composite. In the hybrid composite, we know that short fiber can, like earlier as I showed, can increase the fracture strength, but they are short. So once the crack develop, they do not have as much on a long range crack controlling property. So large fiber can do it, but they do not really increase the tensile strength. So you can combine the two and produce the results, which you have a very, very fine crack width and also post-peak ductility. And to show you an example of this, we did a test. These were mortar specimen reinforced with fibers and subjected it to tension. So there will be cracks. And we wanted to see what is the flow property, because most of the time when we use fiber, let's say as a layer, you want it to be protective of a rebar. So you want to make it as impermeable as possible. Now if you use big fibers, as I mentioned, they will control crack, but the cracks will be wider. Finer fibers, the cracks would be much finer. And it also works with the mechanical properties. So here is the stress displacement of plain mortar, which is shown here, and here is this 0.5% of steel macro fiber. And as I showed you, it doesn't really change much, but post peak. Now this is 0.5% of micro steel fibers. We asked Becker to make for us just the microfiber, I think it was 30 micron in diameter. And then of course when you combine them, you can get both high peak strength and strain hardening response. So that was, I wanted to talk about hybrid. So now I want to talk about the precursor of textile reinforcement. I know you have and other people are working on textile. So original idea was by Pier Luigi Nervi, and he used wire mesh, several layers of wire mesh, and intuitively he said that wire mesh will homogenize crack, so cracks will be so fine that you can use the material in that range. And so there are many examples of Nervi design. One of the most famous one is the Opera House in Sydney. There were thin roofing material made out of ferrocement. So later on, I was a visiting professor at MIT, and Tony Naman, he started doing his graduate work, and he wanted to do some. I was in the materials group, and Tony wanted to do something with reinforced concrete. So we said, okay, let's look at ferrocement and see we can give some engineering qualitative reason why cracks are so fine in ferrocement. So this was a paper we published in 71, and what here is plotted is the composite stress versus surface area per unit volume. So bond, higher the surface area, higher the bond, and you will have excellent, you increase the first crack, and that's important, and then you also decrease the crack width. And so here we showed average crack spacing versus specific surface of reinforcement. And you have more and more multiple cracks and more cracks for the same displacement, obviously finer cracks. So that is the basis of ferrocement. And now, of course, as you know, instead of steel wire, people have been using glass fiber cloth, synthetic fiber cloth, as well as carbon fiber. And quite a bit of work has been done in Germany with the textile reinforced with the glass fiber. So this is the basic idea, that with the textile you can have multiple cracking, strain hardening response, and the bond becomes a key point. Even now with textile, with let's say with carbon fiber, bond is an issue. With the glass fiber, bond can be issue because of the coating. So people have been, as I found out at the conference in Dresden, working on how to improve the bond with the surface area. And one of the reason I mentioned to somebody, we could check whether dipping the glass fiber cloth in a slurry of nanosilica would help improve the bond, because nanosilica might. But with the coating, I'm not sure, but it's many ways to do it. Okay, so now with the development of self-consolidated concrete, we can use longer fibers and higher volume, because with self-consolidated concrete, material flows like water. So that has changed the previous thinking that we cannot add more than 0.5% or 1%. So we can add higher volume of fibers, longer fibers, and that has led to what we call ultra-high performance concrete. So ultra-high performance concrete has no aggregate, primarily silica sand, and compressive strength can be as high as 200 megapascal. In fact, ACI, American Concrete Institute, defines UHPC as minimum 145 megapascal and sufficient ductility. It's very important because ultra-high performance will be very brittle, almost like glass if you don't have fibers. So, but as a result of the development of fiber reinforced concrete and HCC, we have now UHPC. And I just want to show some very recent work I was involved with. This was at Hong Kong Polytechnic in Hong Kong, where we use high density polyethylene fiber, the high density of a higher modulus, and a longer, we can use longer length and finer diameter. And you can see the interesting thing is that the strain here is 8%. You don't expect multiple cracking to have such a high, and the peak, this is in tension, peak tensile strength is as much as 16 megapascal. So because of now we can control rheology, we can add, then these are 2% volume of the fibers. And I thought would be interesting, and we also put that in paper. Here I have shown the UHPC compressive strength versus tensile strain, because compressive strength, we want high compressive strength and we want high ductility. So the work we did, we were not able to obtain 150, but it's more like 120 megapascal, but considerably higher strain. And if you look at the same results, same tensile strength versus tensile strain in tension, because this is considerably higher compared to what has been done. So that's, I'm pointing this out, that now really with the development of rheology and fibers, we can produce both strain hardening composite with relatively large strain and high compressive strength. So this is where we are as far as, I would say, let's say microfibers and macrofibers. We have a conventional fiber reinforced concrete, for example. A lot of work has been being done here with what happens in a cracked concrete with time in creep. And UHPC, which quite a bit of work being done, very high strength concrete up to 200 megapascal and 3 to 4% of fibers. For example, Lafarge has developed a product they call ductile, which is the same idea, but now UHPC has been using in many applications. But the conventional reinforced concrete, reinforcing bar or pre-stressing, they help structural ductility. So after the crack is formed, reinforcing takes over and we can get substantially higher load and ductility. With fibers, the main emphasis is in crack control, and if you have a UHPC, then in some applications with very thin member, very high strength, you may not need conventional reinforcement. However, we know cracks really start at the nanoscale. The most brittle component is cement, and the voids in cement, capillary pores, and even gel pores are at nanoscale. So people say, why not also consider reinforcing it at nanoscale? And the idea is that if you really want super impermeable concrete, so you have a ladder reinforcement. You reinforce conventional reinforcement, micro reinforcement, and reinforcement at nano level. So many people have been working on nanofibers, primarily carbon nanotube and carbon nanofiber. People also have been working with graphite and graphene and graphene oxide. We started working with carbon nanotube many years ago when I had a Greek student, Zoe Metaxa, and she said, I've heard about nano and I want to work on nanofibers. So I said, okay. So we started looking, and like that time, many other people, we were thinking of conventional reinforcement, so we started adding 1% or 0.5% of carbon nanotube. Well, first of all, we found they're very, very difficult to make, because we are talking about nanoscale with huge surface area, and results were not promising. Well, it turned out that Zoe, by accident, made a mistake, and instead of 1%, she added 0.1%. And she found out the 0.1% had the best results compared to 1%. So then sort of light stuck, and we said, if you want nanomaterial well dispersed, then we have to use very small amount. So then of course now most people are using very small amount, and dispersion is still a big issue. We are using surfactant and ultrasonication, but we find out that we still don't have really good handle on dispersion. We measure dispersion using UV spectroscopy, but the slight change in a superplasticizer, even with the same company and a brand name, could change the dispersion. And so, you know, we are trying to see whether we can have a better control, but we know that we can disperse it well. So I want to show you some results of well dispersed carbon nanotube. We have been also using carbon nanofiber, and carbon nanofiber are somewhat more coarser, and the way they are made, we have not checked it, but we think the bond could be somewhat better. So here to show an example of what happens if they are not well dispersed fibers, they all, you know, they conglomerate, but then well dispersed, then we have individual, in this case multi-wall carbon nanotube. This is with the SEM, and there are really not very good way to find dispersion of carbon nanotube in hardened material, because you don't really see them very well because they are at nanoscale in SEM. In an aqueous solution you can with this UV spectroscopy. So the idea with carbon nanotube reinforcement is not that you like conventional reinforcement. You have an aqueous solution where you, in the factory, you have a ultrasonication and surfactant, and then you just use that as, and similar to superplasticizer. So that's a different way of processing. So I want to show you some results with carbon nanotubes. So these are fracture tests, and these are mortar specimen with water to cement ratio 0.5, and these are 0.1%. And if you look at carbon nanofiber, for example, we have substantially improved, almost double the fracture strength, but also maintaining a very good post-peak response. Now we know that carbon nanotube 0.1%, they are well dispersed, and we say, well, why is it working so well, such a small amount? And that time we had our MIP, but the Northwestern was saying, no, we cannot use it because one of the students had spilled some mercury. So we said, we couldn't measure it. So we said, well, what else, what property can be substantially different because of change in nanopore? So we measured autogenous shrinkage, and we found out a substantial difference. So this is a water to cement ratio 0.3, and you measured it after time of setting. And so this is the plain cement paste, and this is with very small amount, 0.048%. So substantial reduction in autogenous shrinkage. And we are still trying to understand why this is so. Then we use this ring test and autogenous shrinkage, measured the shrinkage when the crack starts and how wide they are. So this is the plain mortar, and this one with 0.05% carbon nanofiber. So crack starts later in the ring, and once it starts, it has a lower crack width. So this combines in a way the advantage of both fibers and shrinkage reducing admixture, because we have reduced shrinkage, as you can see, and reduced crack width. Many people have been talking about so-called smart material. So you take advantage of piezoresistive property of adding carbon nanotube. You know, piezoresistive means you apply stress and the resistance change proportionately and repeatably. So like a sensor. So we did some work where we measure the resistivity. This is the work was done at Ultrahigh University in Nanjing, and multi-volt carbon nanotube, what is the resistivity without any, and you can see at 0.1% conductivity has doubled, I mean 2 orders of magnitude, not double, and or resistance has gone down. So that's very effective for using this material as a sensor, and many people have done work. This is not our work, but somebody in a highway department in Minnesota. So this is a cement in 0.1% carbon nanotube, and you apply compressive load repeatedly and remotely measure, calibrate the change in resistance. So when you embed this as a sensor, when a car goes through, the change in resistance, and second car, and you can measure, for example, the speed of the car remotely. And there are many other ways that people can use this as a sensor. So that's another property of carbon nanotube. Then I want to conclude with some very interesting direction. So last year, about January, there's a big ready-made company, I think called Prairie, and before, when you were there, it was Material Service. Now it's one of the largest. So they call a workshop, and they said that the tall building designers are asking that they want to double the modulus of concrete. We are talking about 55 gigapascal, and the reason, so there were people from material suppliers, ready-mix, contractors, and they say currently to satisfy the requirement of modulus, they are increasing compressive strength. Instead of, let's say, they would be happy with, for a tall building with 100, they are using 140 just because of the modulus. And that's a more cement, not sustainable, and also material is more brittle. So after that, I realized that most of our work was on cement and carbon nanotube, because we are talking about nanoscale. But we had seen increase in modulus. So we said, well, let's see what happens, whether we can increase also. What is the increase when you have mortar, sand, and aggregate? Now you realize if you have aggregate, then carbon nanotube is not doing anything to aggregate, so proportionately increase in modulus would be less. Well, we did this. Oh, before I go there, so currently, this is the, for example, from the code in Hong Kong, modulus versus compressive strength. And so if you want, let's say 50 gigapascal modulus, we are talking about 150 compressive strength. So keep this curve in mind, and people are trying to do better than this curve, but still you need high compressive strength to get that modulus. So we went and did this with cement, paste, mortar, and concrete. So look at this. This is the modulus in gigapascal, cement paste and unreinforced and 0.1%. But look at it, in same amount of carbon nanotube, the increase in mortar is even higher. This is you cannot cannot model this with composite material approach. Same thing more or less with concrete. And I will show you why this is, but so we thought that this is quite interesting. So we plotted this, our results with concrete cylinder and 0.1%. So this is the curve I showed you before, and we didn't really change much compressive strength, but substantial increase in modulus. And if you want that modulus with conventional approach, then you need that much compressive strength. So this is, I think, exciting development, and recently we the spelling is wrong, uncoupling in Concrete International we had published. So the designers seem to be quite a bit interested in this, and we will see. Of course, the challenge is we have only done this in the lab menu, and to do it for concrete, we are talking about large, even though 0.1% for a ready extract. So you need a larger facility to ultrasonicate, and so scaling up is always a big problem. So we will see how it goes, but I thought this is very interesting. So now, why is small amount of carbon nanotube increase the modulus? So first let's look at cement paste. So for cement paste, we did this nano indentation. Some of you are familiar with it. So you measure at the nano scale by using the indentation, and from load deflection, unloading, loading, and using contact mechanics to calculate what's the modulus of nanophase. So this is essentially the modulus of CSH, and so this is cement paste with water to cement ratio 0.5, and this, for example, is cement paste with carbon nanofiber. So you can see that we have moved CSH modulus to the right. So carbon nanotube has improved the stiffness of calcium silicate hydrate. So this is why, one of the reasons why, even with a small amount, 0.05% of carbon nanotube, you can see the increase in the modulus of the composite. To see what is happening with the aggregate, we decided to measure the modulus at the nanoscale of the interface. Now you know the interface is 10 to 15 micron, so you cannot use conventional nano indentation because indent itself is few micron. So we are using atomic force microscopy needle, and it's applied in the cyclic loading. So you would essentially measure resonance frequency, dynamic frequency, and so, and also the force is very small, and we can measure the spacing is much smaller than with conventional. So doing this, I want to show some average values. Of course, there is a histogram. So this is the average increase with addition of carbon nanofiber of cement paste and interface. So one of the reasons why mortar and concrete were proportionately more effective is that the interface modulus increases. So you not only increase paste but also interface. But we have to realize when you have let's say fluid silica fume, it also densifies the interface. But silica fume increases the compressive strength and makes material more brittle. Here we don't really increase much compressive strength, and as I showed you before, material is not more brittle. Then another interesting thing we found, we did with the SCM and EDS, and this is the work done by Yuan Gao, the current PhD student, that she took several lines and measured using calcium to silica ratio. So these are average results, and what we found that at the interface, the calcium to silica ratio is lower when we have carbon nanotube. And we know lower the calcium to silica ratio, higher is the modulus of CSH. And I quite don't understand it, and I presented this at one of the conferences when Karen was there, and she said she thinks that the carbon nanotube may influence the crystallization of CSH. So that may be the reason, but we don't know, but we are just looking. But it's very interesting that if carbon nanotube also changes the morphology of calcium silicate hydrate. So that's really the modification at the nanoscale. So that's really a good direction to do it. So just to summarize, what do we want in ultra high performance fiber reinforced concrete? Well, I think we want enhanced modulus of elasticity. Clearly that's very useful in tall building design. We want what I put higher bend over point, that is higher elastic limit. So we want crack, noticeable crack to start as late as possible. Very important, we want strain hardening response, and in the strain hardening response we want during strain hardening sequential multiple cracking, that first crack, second. So during this sequential multiple cracking cracks don't open because there is no noticeable debonding at the interface. Only after the crack saturation the crack width becomes. So that's important. So many applications you want crack width in micron range. We have shown and other people have shown that, let's say, for a cover concrete 2-inch or 50 millimeter thick, cracks 50 micron or less material is impermeable. So that's one way to control it. So I hope that I have given you some idea about what is the current development and what are the precursors, how we reach there. It's very important for us to know. So that's my last slide. Thank you.